video like screencast it just in case. So let's see where we will be like last time. Actually, we kind of like go through some of these definition and some proof of the entropy. We just like kind of show that why entropy is defined that way, and then we also look into the differential entropy. And we also like just before we left last time, we kind of look at like how we connect differential entropy with the conventional entropy, the discrete one. And it turns out it's just by this simple kind of relationship way. So after the quantization, the symbol we can talk about the discrete entropy, and the discrete entropy is just equal to the differential entropy minus the log the quantization step size. And we also gave an example. Basically, if we look at, let's say, want to just store the a packet processing time, and is let's say it's like exponentially distributed, like with some parameter 1 over lambda, parameter lambda is equal to 1 millisecond inverse, and so therefore the mean is basically just 1 millisecond. And so we showed last time that okay, we can then compare, let's say if we quantize this with a quantization step size of 0.01 millisecond, and we try to store this information, like for each of the symbol, like how many bits does it need to store this record. And if we do this using this equation here and go for the approximation, then basically after the quantization, the discrete entropy is just equal to this differential entropy T. T is basically the original continuous random variable minus log 0.01. This is approximately 7.64 bits. So it means that you need around like 8 bits to store this quantized information. And so let's continue today like with some new things. So we'll first start with the Jensen inequality. I'm not sure it should be Jensen or Jensen, but anyway. Let's create a new page again. So so we're going to talk about the Jensen inequality. So basically, it's a very generic, like very general inequality. What it say is just like if you have a convex function. So let's say if I have a function f like this, it's convex. So therefore, have a bowl shape like this. And let's say I have a f here. It's a kind of a kind of like a scalar function. I mean, let's see. The argument I think can be vector, but here, of course, I'm just showing like a 1D like scalar function for f here, but it means that it's possible like this is like a 2D, like maybe the x here. Let's say I write x here. Here's fx, right? So I can have a x is like a vector, so or like you can think of this as a x axis and a y axis, and this fx here, or can we think of like fxy? So we have again like a bowl shape somehow. So So, oh, okay, by the way, like, I'm not sure how much you guys know about convex function. So a function is convex, basically have a shape like this, or in the sense if you draw any lines between here, it's actually not exactly convex the way I draw it. So if it's hard. So if it's convex, basically if I on the surface here, of course, if it is a, in this second case, it's really a surface, or like if I connect any points on the function, basically draw a line there. The line it will be always above the projection of that function. I mean above, for example, I can look at this line here. It's above like this function here. As I said, it's not exactly very convex because I look at this 2 point here. This line maybe, yeah, but anyway, you see my point here. So, and it's the same for like the high dimensional case, right? For example, if this is a bowl shape here, then it's hard to draw actually. How do I draw it? Like something like a bowl, like something like that. If I look into this bowl here, if I pick any 2 points on this bowl here, maybe these 2 points here, and I connect them, and I look at like the corresponding value of fx on this line here, and this straight line should be above this f of this line here. Or of course, like this line, let me be more precise. Let's say this is a 1 point here is x1 here, and there's another point here is x2 here. Then I will have this line here is basically like some lambda x1 plus 1 minus lambda x2 f of this, right? And this line here, and of course I need to specify lambda should be between 0 and 1. So then you see that like basically this cover like this line here, right? So maybe I use another color. This will cover this line here. Now, then you look at the function here. This f something here is less than the value at this location here. So therefore, it's less than the so it's less than the linear interpolation of this line. So this, oh, okay, yeah, I actually, I didn't draw it very well. I should say, this value here, f of this guy, is basically this line here, right? Let's see. So someone is trying to join. Is that okay? Let me see. Actually, are you guys prefer to do it this way? Actually, I'm in the classroom, so if you guys are okay, like doing like Zoom like this, I will stay in Tulsa, if you guys don't mind. So I guess next time I will also like maybe like teach from Tulsa, because my other student will show up, like it's actually a bit easier, like to at least have someone like kind of a present, so I can have some immediate feedback, because now I'm not quite sure like whether you guys are following or not. So but let's see. Why I'm trying to get you in. Let's see, how do I get you in? There's some more here. Oh, here I see you. So okay. I forgot how to spell or pronounce your name. Pia or something like that. I guess like you should be able to see the screen now. So so we are talking about Jensen inequality. So is basically Jensen inequality is just something like if you consider, okay, I'm talking about converse function first. Actually, I want to explain like what do we mean by converse function. So for example, I have a function over a vector space here, like, so it's a, for example, in this two-dimensional case, x and y here. So a function is converse. So if I have, basically, if I consider any 2 points on the surface of the function in the high dimensional case, and I consider, interpolate along these 2 points here, and I look at the value of that function. So these f values should be less than equal to so less than equal to the linear interpolation f x1 plus 1 minus lambda f x2. So basically this is this line here. So just this line should be above this. So then this function will be converse. And in two-dimensional case would be, again, it will be like this. This line is above like this function here. So if I have a function is converse, f is converse, then I will have the Jensen inequality or Jensen inequality, basically just expectation f x is bigger than equal to f expectation of x. So I'm not going to prove this one, but I guess we can pick some special case to think about that. And you see it's pretty obvious that this is, or like I shouldn't say obvious, it's it's kind of intuitive, like why this should hold. For example, like if I look at okay, Ben is also like trying to get inside. Let's see why here probably. Oh, here. Now, okay, Ben also came in. So I see like I'm talking about Jensen inequality again. So we have, if the function, we have a function f which is converse, is satisfy this inequality here. So basically, like if you connect 2 points on the function, and then like the line of that interpolation is above the curve of that function, then we have the Jensen inequality. So it's given by like x. Basically here x is a random variable. Like f of x, of course, is also a random variable. Therefore, we can compute the expected value there. And again, like f supposed to be have a scalar output. So like therefore, this is just a number. And I can also, which is bigger than equal to the f expectation x. If you think of some special case, obviously it will hold, right? Because, for example, if I think of x is just, like it's do you have any question? Like, let's see. Yeah, okay. So Ben, it's good like to hear you. Like, so if you have any question, just let me know. And yeah, and so by the way, like I probably will leave homework today also. Like I will see like either it will be due like next week or like the week. I will see like how much I put into the homework. Probably will due next week. So please check. Oh, and by the way, for homework, like I will just use Canvas. So you see, most of the time I don't use Canvas at all, right? But for homework submission, I guess it's easiest to use Canvas. So you can just submit to Canvas and that's it. Jen, yes.
Could you put it on your course page or the Canvas, the homework?
Homework, I will have a link on Canvas. The homework itself, I probably will put on my website. But you will submit on Canvas. Yeah.
Sure.
Yeah.
Sure. Thank you.
Yeah. So let's see. Yes, I'm saying like I won't actually show the Jensen inequality kind of like rigorously, but I'll just like argue that it's quite apparent it's true. So maybe I give some simple example, like let's say when x is kind of a random variable that just takes two values like x1 and x2, let's say, and if take x1 have a probability like p, and then have x2 with probability 1 minus p. Then if you look at this case here, like what is like f expected, or like maybe I start with this expected fx here will be just equal to what is equal to fx1 with probability p plus wait, yeah, and then plus like 1 minus kind of like fx2 with probability 1 minus p. And how about like f expectation x? So f expectation x will be just equal to expectation x will be p x1 plus 1 minus p x2, right? So because I with one probability p will be x1 and probability 1 minus p will be x2, so it will be just this one, and f of this is that. So then you see that like basically this is bigger than this is just the definition of like convexity, and you can generalize that like when you have like more than and basically if you have 3 points, let's say like x is equal to x1, x2, and x3, let's say with like probability p q and 1 minus p minus q, something like that. Then you have like 3-point case and somewhere like this is like 3 points here. Then again, like if you do a linear interpolation, I'm not going to go through that, but if you think of like what will be your f expectation of x, it will be just basically like it be kind of a point, depends on like how your x is, how your pq is distributed. It will be like some point inside this region, right? Some point inside this region, and f expectation of x will be some point like here, so it will be some point here. And on the other hand, your expectation, oh wait a second, f expectation, yeah, my expectation f of x will be basically just this point here, right? So this one is my expectation f of x here. So again, obviously like this will be like kind of expectation f of x will be bigger than f expectation of x. So I mean, of course, you can use induction to show that like for any kind of like discrete distribution, like Jensen inequality will hold, and then like since all discrete case will hold, and then like you can do calculus, and then to extreme case, therefore continuous case will hold as well, stuff like that. So but I'm not going to prove that. But it's I mean the inequality itself is very intuitive actually. So any question with that? So, but it's very intuitive, but at the same time,
Please say your name after the tone.
yeah. So, like, I guess, Spanish, is that? Do you have some question? Hello? Oh, yes, someone is calling. Wait a sec. Hello?
Hello, Dr. Tang.
Oh, hi.
Yes, yeah, this is Benny. I already opened your meeting, but I could not connect to the room. So what should I do, sir?
Oh, you don't need to connect from the room. Are you going to connect from the laptop or something?
Yeah, already connect to the laptop. I mean that already opened the laptop, and then just click the link that you are sent via email, and
Yeah.
then there is no connections. Always uh, running it something like this. So basically cannot connect to the meeting.
Wait, okay, I see that you are connecting from somewhere else. Can you
Oh
work
yeah,
now?
yeah. I can see now. Yeah,
Okay, yeah, I see
I
that you. Oh,
yeah.
okay, yeah, you have two connections. You can see, I don't know why. So, maybe it's from
Yeah, no, already connection now. Already connect.
somewhere. Okay, so then I guess that's fine. Okay, yeah, okay, I'll continue then. Yes.
Okay, thank you
Okay,
so much,
okay,
sir.
okay, bye.
Bye bye.
So let's come back to what we have here. Uh, so so yeah, we are saying like, okay, this is like the Jensen inequality is pretty obvious, but very useful. And I'm just saying like, if you guys have any question about that. Let's see, where am I? What's next? So okay, we'll use the Jensen inequality to, for example, to show the upper bound of the entropy, the conventional entropy, the upper bound. So let's say if I have some random variable x here, it's just a discrete random variable, and basically hx will be bounded by log x. So here my log assumed to be log base 2, so the unit will be base here. So of course if I use log base e, maybe then if I use ln, then this unit will be let or something like that. So again, I mentioned last time like the difference using different log, because you know that like if I log base 2 something, x is actually just equal to ln x over ln 2, right? So it's just it only differ by a scalar factor here. So therefore, if you differ by scalar factor, it's basically just there's a difference of the unit. So therefore, okay. Anyway, right? People just introduce different units for different log. And okay, we say that like we will have an upper bound if like for a random variable x, the entropy will be bounded by log x. So let's just prove that. So we have hx is equal to expected log x here. Right, this is just a definition of entropy. Oh, sorry, log px. I'm missing expression log px here. Just the definition of the entropy. Now I can, of course, write it as a expectation log 1 minus px. And now what we observe here is like, oh okay, by the way, like for the Jensen inequality, like we have this converse form, like when the function, if f, the function is converse, then we have this. Apparently, for the same argument, if you have a function is concave like this, if f is concave, if this is another f is concave, or maybe let's call this g here, g is concave. Let me have a let me draw a little bit concave shape here. This is a concave g here. And apparently we have like g expectation x. That is basically using the same argument, just everything opposite, right? It will be bigger than equal to expectation gx, stuff like that, right? Now back to here. So I'll just say have both forms. I don't know which form I'm using here anyway, but we'll have both forms here. So log function, yeah, actually log function is concave. Like this is a log function when it has a shape like this, right? Yeah, it's a concave function, so therefore like expectation log this guy here should be less than equal to log expectation 1 over px, right? But if we look at like what is expectation 1 over px, let's write it down. Like it's px. I'll probably be careful with my symbol. Like 1 over p small x here. This is actually big x here. When I do expectation, supposed to be this is a all big x here. 1 over p small x sum over x, right? So x is a sum over all x. Basically, like that's sum over all x in the alphabet of x, right? And so this got cancelled, it will be just 1 here. So it's basically sum over 1 for all x inside the alphabet of x. Therefore, basically, it's just counting the number of the size of the alphabet of x, right? So therefore, this is just equal to x like that. So therefore, like this is log x. Yeah. So this is, of course, this is like by Jensen. So any question here? So also let's just look at several examples for this simple upper bound here. Let's say if like I have x is binary. Let's say for example flipping a coin, I only have 2 outcomes. Then the bound is saying that like it should be less than hx, like the number of bits to store this information, this binary information, will be just less than log 2 output, right? It's just 2 outcome here, it's just equal to 1 bit. So it's apparent, right? If you have like 2 outcome, I don't care like how you massage this distribution, like you always can use just 1 bit to store this information, right? And let's look at another example. Let's say if I have a dice here. So a dice will have like y is like outcome of a dice here. So I guess one of you guys, if you don't want to say something, probably want to turn down your mic or something. Like there's quite a bit of echo. Let's see. There's the. So anyway, I don't know how to. So let's see. That's very weird. I don't know how to find the but it's okay. Like I guess the echo is gone. So so for example, if I have dice, then there will have like 6 different outputs, right? 6 different outcomes. So, oops, what happened? So I have like hy, let's say, is less than equal to log 6. So, and this will be like less than 3 bits, right? So if I want to just store like the outcome of a dice, I just need less than 3 bits. And I guess it's apparent, right? Because 3 bits can store like 8 different outcomes. Of course, this is like totally obvious. So anyway, let's see. What next? Oh, actually, by the way, I forgot. Like last time, we also talked about like for multivariate Gaussian, we compute the entropy for that, right? And so just have a review for that reminder. Like if I have like something is Gaussian, let's say X is Gaussian with like, I will just denote like this, like with mean mu and variance sigma, covariance matrix sigma. So it's a multivariate Gaussian. So of course, the ordinary Gaussian that you came across often will be just a special case of this multivariate Gaussian, and the differential entropy of this one will be just log 1/2 determinant 2 pi multiplied by the covariance matrix. And be careful, like I don't think if I mean like, I just want to point out like here is an obvious remark. Your entropy is measure of uncertainty, right? Stuff like that, the amount of information. It doesn't matter how to map the outcome. So therefore, like the mean is totally unrelated. It's not important. So only depends on the shape of the distribution. Like for example, whether it's like this shape or like this shape here, or like all sharp, and and so it doesn't matter like where you have this distribution. Like for example, if it's your distribution here, you have same entropy. Like if your distribution shift to, let's say, here, assuming like I'm not very good at drawing, assuming these two have the same shape here. So and okay, this is an upper bound. We just mentioned that, like it's an upper bound of entropy, but it's for a discrete case, right? Can we do an upper bound for the differential entropy? Let's say if we have like some see, I need to make a form a new page again. So let's say I have a kind of like now a continuous variable x. I want to again make them upper bound, so I want to look at hx, like some upper bound on hx. So what do you guys suggest? Of course I can't hear you. I don't know whether I can hear you or not. I guess only Benny's mic is not mute, so I can hear you. BR also, I see you unmute the mic.
Yeah.
Yeah. So I mean, like, can we find the upper bound? I mean, or like, should I say like what's the upper bound for x? Like, if I just say like it's some continuous x, like what's the upper bound of hx? Okay. I mean, like, first of all, like if you think of like the derivation we went through, it also applies to differential entropy, because let's say if I write differential entropy hx, also I can write it as an expectation. Sorry, yeah, expectation of, I can write as expectation of minor log px, right? This actually hold for both like differential entropy and like the original entropy. And of course I can go through the same thing. I can write this as like expectation like log 1 over px. Then I can again I say, okay, using Jensen equality is less than equal to log expectation 1 minus px. And so therefore, like again, it will be less than equal to log. So now in this case, this will be expectation of px will be like an integral, right? Integral 1 over px and px dx for all x in the kind of the domain of x, or like the support of x basically. That will I can again like define this as x, something like that. So basically this is not a very interesting bound, because in general, for example, if you have a Gaussian distribution, your support will be infinite, right? You can go all the way to infinity, even though it kind of like diminish pretty quickly exponentially. But this bound, if like x is infinite, then like this is just like some infinite value, right? So it's not a very interesting bound like for continuous random variable. So in the sense we want to make have like more interesting bound, one thing we can do is like we impose like some more constraint. So for example, like okay, I don't know what you guys will think. Like, okay, maybe I can constrain the support size, but it won't be too interesting, right? For example, I say the support is like only from 0 to 2. So everywhere outside, I will just I need to force the distribution to equal to 0. I mean the probability that it's less than 0 or like bigger than 2 will be equal to 0. This is not very interesting, as you can see, because many very common like distribution won't kind of satisfy this kind of like very restrictive condition. So instead, like we can make a constraint, let's say on the. Okay, what do you guys suggest? I want to hear something from you guys. So let's see. Danny, maybe you say something? Like Danny, are you still here? I guess he probably like is not here or something like. So BR not here?
I'm here.
Yeah.
I'm thinking.
So but is my question clear? Like I mean like I probably want to have some constraint to have some bound. I want to have some upper bound for the differential entropy. And I want to impose some constraint on the distribution. Yeah, actually, just think of like when you think of random variable, um, when you have the distribution, like it specify everything, right? Or like I should say, like you cannot know more than the distribution regarding a random variable. So after all, it's random. Um, all the statistics you can get is from the distribution. um, and so that's and then afterward, like if you want to just say um, uh, just get a little bit information like then about a random variable, uh, I guess the first thing you think of is this uh, what should I say, like something you learn like in the first class in statistics, for example, like the mean and then variance and so on, right? And in general, it will be like um, when you have mean and variance, is basically just an expectation of the first order of the variables and then the second order. When you think of the variance, it's basically it's like just it's really the second moment, but like we kind of adjust it a little bit to be more meaningful, right? Like x minus expectation x, this guy here, and so what I mean, like for example, like we may kind of like constrain with a fixed mean, but of course, as we mentioned already, like if we constrain a fixed means, it won't be very interesting because like it doesn't really the differential entropy like depends on like the mean at all. So so actually the first natural things we can be like, okay, let's fix the variance, because after all, what is variance? Just like the spread of the distribution, right? So let's say if I one interesting question to ask is like given a continuous random variable, and let's say if I have its variance given some sigma square or something, like let's say it's like 1D random variable, and for a variance like this will be like I don't specify the shape, then it will be kind of like I can either have this, maybe like I have a sigma square variance, and I may have like a different shape, maybe like is sharper. I don't know how to draw it, but kind of like eh, oh, let's see. I guess how I draw it should be like this. So let's say this is a go to 0. This height is 0 here. So I may have like a different distribution that is like sharper in the middle, but does not decay as quickly and have the same variance, I say. So maybe this guy maybe decay later on. Also have a variance of sigma squared. Yeah. So so it turns out like okay, I will show that later. Actually, I will digress a little bit, just following my notes. So if I have a random variable x and when sigma square as a constraint, it turns out that the differential entropy is maximized. So hx is maximized. How should I say? Wait, maximize when x is like a Gaussian. So it's like when x is maximized when x is like a Gaussian with that variance. So therefore, like if we just from what we call earlier, for differential entropy, the Gaussian for Gaussian random variable, the differential entropy is given by this. So therefore, like it's just this is a square Oh, I already immediately forgot like what is that. Okay, log determine 2 pi sigma square. Okay, so I have log here. So if like is 1D, there's no determinant there. So just 2 pi sigma square. I think it's missing something. That should be E somewhere. Let's see, 2 pi. Okay, I guess I probably I probably missing something. Probably has a E somewhere here, I think. Yeah. But anyway, like you just can just say look at the nodes and yeah, 2 pi E sigma 0. So I probably should make a correction of my, let's see. Oh, actually, my slides are correct. I just say when I copy, I forgot the E, so it's fine. So, but I will just kind of keep this in suspense. How do I say it? I'll come back to this one later on, like why Gaussian will be basically the one have maximum entropy given a fixed variance. But now I digress a bit. So because I probably need some of the result to going to prove this. So I'll talk about like joint entropy first. Just expanding like some of what we're talking about, like about the regular entropy. So for example, like if I have like X, now I can have actually I can talk about like instead of like the entropy of one random variable, I can talk about entropy of like 2 random variable, right? But of course, you can also think of like this as a joint variables, right? It's a bigger label, like for example, x, y. If it can take x can take a value 0 and 1, and y it also takes value 0 and 1. Then like x and y together can be like a bigger label that, let's say I have value 0, 0, 0, 1, 1, 0, and 1, 1, and so on, right? So then of course you think of that way, like expectation entropy of xy is just like again like expectation minus log p xy, right? And this is just okay, just very reasonable. We can extend that even for like more than 2 random variables. I say I have x1 up to xn. Again, it's just equal to minus expectation log p x1 up to xn. So this is getting cold here. Just try to put on a jacket. So now for differential entropy, we do the same thing, right? Basically, it's exactly the same thing. Like I have hxy. It's actually exactly the same expression here. It's expectation log pxy here. But of course, this p is like the PDF instead of the PMF here. This is PMF, a probability mass function. This is a probability density function here. And the same thing, like x1 up to xn can be expectation minus log p x1 xn. So exactly the same thing. Now so we have the joint entropy. Now what we can do next, I want to introduce the so-called conditional entropy. conditional entropy. So let's say I have again a hxy, just as what we wrote above, is equal to expectation minus log pxy, right? Now, but I can actually expand this pxy, right? In general, like xy, I don't care whether, okay. If I expand that, by the way, like this expand that, by base rule, it would be something like right, px, py given x, right? Something like that. Or of course, I can also write py times px given y. So I can take either form here. Let's say I take this form here. So then it's equal to expectation minus log px minus log py given xy. So this guy is just equal to hx again, right? And then for this guy here, I have something like this. It's like expectation minus log py given x. Here, I will call this guy like hy given x, basically. This is the conditional entropy of y given x. So to be more kind of like specific, like this guy here, the expectation here is something like this way. Be very careful, like because I have like y and x here, like both y and x are random variable here, because I start with like x and y are both random variable, right? And I just do a simple expansion of like the log, and I'm writing like pxy as like px multiplied py given xy. So still like all my y and x here are random variable. So therefore like I need to be very careful. This is sum over both x and y when I expand this. So it's like p xy log py given xy, something like that. And okay, one thing I want to maybe I probably show later on, but let me also specify this here anyway, since I already writing like this. And I can write like let's see, pxy here I can write as a px py given x also, right? Log py given x here, sum over xy here, minus. So this is something like minus sum over x px, sum over y py given x, log py given x. Actually, probably better to put this minus sign inside here. So if you look at this guy here, this is like really the entropy of like hy given small x here. If you can think of like, okay, x is like a parameter here, right? So the parameter kind of like adjusting the distribution of y. So for different parameter of x, you have a distribution of y. But y itself is still like a distribution. What I mean is like, if you look at py given x here, I sum over py. I mean, if I sum over y here should be equal to 1. Right? This is like a valid probability distribution. Just like when I have different x, will be like different distributions and so on. So this is a totally reasonable like definition. That we didn't actually introduce any new definition here. This is just the original kind of, you can think of like, this is like a convention write this way, but you can even like think of writing like this way, y small x, or like y, maybe I put a parameter x here, something like a comma. So it's like for a y or maybe even maybe like hy x here, maybe something like that. Like the I have different x basically different y, something like different different random variable of y. So then I look at the entropy of that. But no one uses this convention, by the way. This is not a simple notation that you will see, like no one will use that. But you can really think of this that way. Then it's just equal to this one here, right? And so therefore, like if the conditional entropy here defined this way is also is just the average of the entropy of y given small x, average over the distribution of x. So it's like very natural, right? Something really very, very natural. And let's see. And of course I can do the same thing, right? I can exactly do the same thing. I'm like x, y. If I go for the entire nothing is different here actually. Everything is the same. I can also make up the same conclusion that like I can define hy given x. The conditional entropy of y given x will be like, oh, essentially actually okay, maybe I can put put this on the other side. Then I can define hy given x as like xy minus hx. I'm saying I'm the same as this one here. But of course, I think this is also like you have a nice interpretation, right? What you can think of is like what's the amount of information or uncertainty you have for both random variables x and y. It will be like the amount of uncertainty of x plus the amount of uncertainty of y knowing that what x is now, right? So it's like very natural. And of course, we can expand this. For example, if I have like h, maybe I use the original discrete case, like x2 up to xn here, maybe just equal to hx1 plus hx2 given x1, and so on and so forth, to hxn given xn minus x1, x2, xn minus 1. Something like what's the amount of information for like x1 up to xn will be like first the amount of information of x1, then knowing x1, what's the amount of information of x2 knowing x1, then what is the amount of information of x3 knowing x1 and x2, and so on and so forth. And of course the same for differential entropy, like this all big H I can replace by small h and it will still hold. So now let's just go for a very simple example. Let's say I think like that's an example we had like in the first class or something. So but I guess the values are different. So let's say what's the probability that it's going to rain tomorrow, like with a better, yeah, someone is going to. So anyway, it's probability like rain, and then I remember to bring my umbrella. I think like this is not a very kind of good example in the US. No one actually bring umbrella. But anyway, so so let's say like tomorrow to rain, I'm like I bring with an umbrella, it's like 0.2, and then I say like tomorrow is sunny, So also like this does not apply well to like Oklahoma. I don't think the probability is so small. Anyway, I'll just use that number here from the slides. And then like probability like going to rain and also like low umbrella is like let's say 0.1, and probability like sunny low umbrella is like 0.5, let's say. So therefore like then I will have like let's say this is the variable W, let's say it's the weather, it's like whether it's rain or sunny. You can take values like either rain or sunny, and then I have whether I bring umbrella will be like with umbrella or like no umbrella, let's say. So then I can, let's say, just try some example like, okay, what's H, W, and U, okay? Then in that case, okay, it will be just expectation minus log P X P W U, right? Something like that. Or it will be like log P W U. Let's use small symbol W U. P W U. Something like that, right? So therefore, like will be just 0.02 log have a minus sign here, 0.02 minus 0.1. Oh, sorry, no 0.02, 0.2 log 0.2 minus 0.1 log 0.1 minus 0.2 log 0.2 and minus log 0.5 log 0.5. That will be kind of approximately 1.76 bits. And I can compute like HW is a minus. Okay, for HW is a similar, right? But now it's only two cases, right? It's either like it's going to rain and also it's going to sunny. So from here, like, what's the probability it's going to rain? Let's see, still anyone is like. Oh, okay. I hope I still have connection here. Do I?
Yes.
Oh, okay. Yeah, I don't know why this part is freeze. Looks like okay, like it came back. So. So anyway, like the probability is going to rain will be just 0.2 plus 0.1, right? So it's 0.3, right? So it's like 0.3 log 0.3, and probability of sun is just 0.2 plus 0.5. So it's minus 0.7 log 0.7 is just equal to 0.88 bits. And HU is just equal to, in this case, with umbrella, the probability is 0.2 plus 0.2 is 0.4 log 0.4 minus 0.6 log 0.6. So it's approximately 0.97. And HW given U, the conditional entropy of like U, W given U will be what? We can just use the equation, right? It's equal to HWU minus HU here. So therefore, it's HWU is this one, 1.76 minus HU 0.97 would be like just 0.79 bits. And also like HU given W is equal to HWU minus HW. So it's just a 0.88 bits. Yeah. So yeah, this is a very simple example. So any question? Like super simple example. Let's see. What should I do next? Yes.
Jensen,
Yes.
how do you do it if you have multiple variables other than just two?
Oh yes. Oh, it would be like kind of similar actually. If you have more than two, for example, like if I have three variables, then I will have, let's say, like if again, like if I can each of that two take two values here, then I will have like eight different possible outcomes, right? Then, for example, if I have the variable is like x, y, and z, and take value like different, so I will have like, if I look at h, x, y, z there, will be like sum over like kind of like eight different values. Yeah, eight terms I add together. And of course, if you get messy, like then you can compute like individual like HW, HU, and so on, and you can look at like HW or like here like maybe X given Y, YC, and XY given Z, and so on. Yeah, that's actually a good question. Let's look at this one. Okay, what is HXY given Z here? So remember, we always have this kind of like, when we have the conditional entropy, it's like something of chain rule here. So this, you can think of this is just like, what's the information of x, y, knowing z? That actually, like you can just spell it out, like it would be like just information of x knowing z, right? Plus, what's the information of knowing y, knowing both like x and z, right? Yeah. So and let's see, and what else I can. I'm actually honestly compute this. Maybe easier to compute this. For example, if I want to compute this guy, this can also be equal to hxyz minus hz, right? Because hxyz is like, yeah, knowing cm then. So this is probably easier to for computing this side. This probably is easier. So basically for all these conditional entropy, you can compute like this way. Just compute the entropy for each of the variables, the joint entropy of all the variables, or joint entropy of like multiple several variables, and then just have some arithmetic combination, and yeah. Yes. So